Welcome everybody to this afternoon session. My name is EdgeColored and I will be chairing the session. So our first talk this session will be an invited talk by Professor Rick Wilson. Rick Wilson got his PhD degree from Ohio State University in 1969, and the title of the thesis was An Existence Theory for Pairwise Balanced Designs. And the reason why I mentioned this title is that it quite well tells you what kind of work Rick is famous for. So he made the theory for the existence of many basic types of combinatorial designs complete at a time when mainly sporadic examples and sporadic families of designs were known when this theory was completed. Most famous for this groundbreaking work in design theory, for which she, for example, received the SIAM Polya Prize in 1975. Rick Wilson has also contributed substantially to the theory of graphs, Latin squares, finite geometry, set systems, algebra, coding theory, etc., etc. But also outside mathematics in engineering. Most of his active career and all of his emeritus career he has spent at California Institute of Technology, Caltech. And finally, I would like to mention that you have a passion for flutes, collecting and playing flutes from all over the world, and it's a great pleasure for me to give the floor to you.
Thank you very much. I will be talking about some of the work that I've remained interested in my entire career. I tried to find something else to talk about, but I thought this would be a very good topic for this audience. First, I want to start by wishing happy birthday to Charlie Colburn. As long as this slide is here, I will wish a happy birthday to anyone who has a birthday this year. And I will say thank you to Charlie Colburn for having a birthday so that we have this nice conference. I'm very pleased to be here. I would like also to thank him for his hard work, his leadership, and breadth and influence on the field of combinatorics and related topics. I admire all of his efforts. So here is the topic of, simplest case perhaps, of the topic of my talk. I'm going to decompose complete graphs into copies of a given graph. For example, everyone knows that K7, the complete graph on 7 vertices, can be the edges. I'm talking about partitioning the edges when I say decomposition. Can be partitioned into 7 triangles. You can consider directed analogs, and the complete directed graph on 4 vertices can be composed into 4 directed triangles. And here's a theorem that's quite old. Given a simple graph, you can construct decompositions of the complete graph on n vertices into copies of G. Maybe Peterson graphs. Yeah, you can't do this all the time. If you have the complete graph on n vertices, you know how many edges it has. And if that isn't divisible by 10, the number of edges in the Peterson graph, you can't decompose the complete graph. But these conditions are necessary and asymptotically sufficient. We can't hope to settle all, given G, to settle all cases, but asymptotically is interesting enough, and it shows we're not missing too much when we show these conditions are asymptotically sufficient. So G here is the greatest common divisors of the vertices, greatest common divisor of the degrees of the vertices. If G is the Peterson graph, then little g, small g, would be what? 3. It's regular, degree 3. And m is the number, that's 10, it's 20, mod 20. But now let's make it more complex. This will have applications. Make it more complex by considering a family of simple graphs to start with. And we want to decompose the edges of the complete graph into copies, where you may use any of the graphs in script G any number of times. For example, you might have the Peterson graph and the second graph, K8, complete graph in 8 vertices. And if you're allowed to use both of these, can you decompose the edge set of the complete graph into copies of those? And more generally, script G is any family of simple graphs right now, and it could be edge-colored graphs. I will tell you more about those later, or edge-colored directed graphs, or edge-colored multi-directed graphs. But no matter what script G is, we have to consider complete graphs of the analogous form. And the theory says there are two integers, a and b. They may both be 0, but otherwise we can assume b is even and a divides b. So that these conditions are necessary and asymptotically sufficient for the existence of the decomposition. I mentioned that these can be assumed b is even, a divides b. That will make them unique. But it may be that a and b are both 0. And then what does this theory say? If a and b are both 0, I think it says that n is 1. That's necessary and sufficient. That means there exists no decompositions, and that can happen. We'll see. This theorem, who proved that? When? I don't know. Oh, that may be Esther Lamkin and myself. I know I'm involved, but I don't know when. But, so the problem is to determine that previous theory is meaningless unless we know what these numbers a and b are. And in this case, they're functions of script G. And here I call them alpha of G and beta of G. And here's what they are. Alpha of G is the greatest common divisor of the degrees of all vertices, and beta is twice the greatest common divisor of the number of edges. So look at this example. What if you have the Peterson graph? Oh, that's don't look at Peterson graph and K8. So these are allowed into decomposition, just simple graphs, and I'm decomposing the complete simple graph. What is alpha? It's the greatest common divisor of the degrees. Well, the Peterson graph, you may use degrees from either or all of the graphs. Both of these are regular, but in general, they don't have to be. But degrees 3 and degree 7, the greatest common divisor is 1. Alpha is 1. And beta is the greatest common divisor of the numbers of edges. Well, Peterson graph has 10 edges. K8 has 28 edges. Greatest common divisor is 2. Alpha is 1, beta is 2. That just means there's no constraint at all, because this is always divisible by 2, and that's always divisible by 1. So the answer is you can always decompose the complete graph into those two. But now I want to talk about edge-colored complete graphs. I'll use R for the number of colors. In this case, R is 4, and I'll use, that's a 4 up there. This is very crude. I've given this talk when I've had a blackboard, and I don't have one today, so I tried to draw these in the PDF file, and I found a buggy piece of software that let me do it, but then I can't draw well with the touchpad. N vertices, there are N vertices in there, you see them, and the 4 colors, and any two, well, 2 of them are similar, but 4 distinct. Any two vertices are joined by one edge of each color. I'm sorry, I didn't do all the pairs of edges. But there are many, many green edges, one joining any pair of vertices. Same for red, yellow, and blue. And consider families of graphs. Which have their edges colored using these R colors. And I will demand that soon, if not here, I demand that the graphs G in a family script G are all simple. Simple means this at most one edge of any color. When I'm talking about edge-colored graphs, at most one edge of any color joining any two vertices. It could be one red edge or one green edge, but not both. And I want to decompose the complete graph where any two vertices are joined by edges of each of the R colors. Now, the complete graph is not simple, of course, but the graphs I'm decomposing it into are required to be simple edge R-colored graphs. And to give necessary and sufficient conditions for the asymptotic existence of these decompositions, I need to consider instead of just the edges, numbers of edges, I need for every color the number of edges of color I. So that's what this vector is. M1, the number of edges of color 1 in G. These are functions of G. Through MR, I have vectors. And then degrees, I don't know, tau of G at vertex X is the degree in color 1 of vertex X, the degree in color 2 of the degree of color R in X. The I is the color I degree of X. So I have to work with these vectors, and instead of, well, here's an example. Two simple graphs. One has 3 black edges, one has 1 black edge and 2 red edges. So what are necessary conditions for the existence of the decomposition of the complete graph with 2 colors? The number of edges of each color is n-1. So if I have 8 copies of the first graph, number of directed edges, let's talk about directed edges. The number of directed black edges in the first graph is 6, in the second graph it's 0. In the first graph, the number of red directed edges is 2, 4. Wait a minute. And this edge, 6. Everything's okay. 2 black directed edges and 4 red directed edges. So if there are A of these graphs and B of those, I have to have these equations, and this means that this number is even, and means no more, because every large even number can, for every large n, this is an interval when you're a combination of those. And there's nothing, the degrees add no new information. Here is a vertex at degree, black degree 1 and red degree 1. So there's no constraint on n-1 from this equation because of that one term. So anyway, n times n minus, this is the condition. This first condition I spoke too fast. For a constant vector to be an integral linear combination of those two, the constant must be a multiple of 12. This you discover with some row operations. It's not hard. This is the definition of beta and G for the theorem to be true. The greatest common divisor, so that the constant vector of those integers is an integral linear combination of those, that's alpha, and beta comes from the edges. So these are necessary conditions. But there's another necessary condition. Can you think of another necessary condition? Watch out for instances where every graph in our family has more red edges than blue edges. There's no way you can decompose the complete graph with red and blue edges, because the complete graph has the same number of red and blue edges. So if you start with let's get rid of those graphs which are unnecessary, and say the family is admissible if it has no graphs that cannot be used here with life. This is funny language. I wish I hadn't used it. G is admissible when there's this non-negative relation here, the family, and useless. No graph is useless. When is useless? When it can never be used. So, I should have said things differently. But here's the theorem, which is not recent, but has applications. I want to talk about some of the applications. I will not spend much time on the proof. The computation of these numbers is just greatest common divisors after you get rid of the useless graphs, and this is a feasibility question when you're programming. So it's not quite as computationally smooth as it would be for the case when you have one color. So here are some examples where that can be phrased in terms of graph decompositions, and I think these are interesting. These examples are all about structures that were the small structures that were already known by other methods, but if you phrase it in this language of decomposition, you can say within a minute or two that you settle the asymptotic existence question, not the entire existence question. This graph corresponds, this is two colors. I didn't use red and black, which is black and solid and dashed. And I'm decomposing the complete graph again. With any two vertices joined by one solid, one dashed edge. Suppose this is our graph G, single graph, we want to decompose it. That's equivalent to what's been called a nested triple system. The triangles X, Y, Z, the triples of these triangles in all the graphs in our family, there will be many of these subgraphs, form a Steiner triple system, because every black edge, every two vertices, in other words, is contained in one of these graphs. But there's also every pair of vertices will be contained in one of these graphs as a dashed edge. C is a center, so to speak. In other words, every pair of vertices, unordered pair of vertices, will occur in two of these graphs, once dashed, once solid. So it's a design, if you like, the four vertices with k equal 4 and lambda equal 2. But there's an outer triangle and the center. This is called the nested triple system. And the question of when these exist is known. Is that Doug Stinson's work? Is he here? Yeah. Yes, he says yes. Wallace worked on those too, I think. No, yeah, okay. But it's a lot of work to settle the complete problem when these decompositions exist, but you can easily compute alpha and beta, very simple, and get the asymptotic existence without any further work once you know that it's a graph decomposition problem. Reverse triple systems, this is something I think Alex Rosa has worked on. And who settled this, though? Doug Stinson has no, you did something else, I know. And a standard triple system that has an automorphism fixing one point and setwise all the triples on that point, but interchanging the other 2 points. So there's a special point, and interchanging the other 2 points on any of the blocks, on all simultaneously, is an automorphism of the design. And that's equivalent to a decomposition where you allow 2 graphs in the family. That's why we wanted to consider the case of a family of graphs. And watch, I'll show you the correspondence. It's explained here, roughly. If you have a decomposition of Kn in this vertical blob, the edges into graphs where you may use these black triangles or triangles with 1 black edge and 2 red edges. You can get a reverse triple system by taking 2 points corresponding to every vertex of Kn and adding the special point and start with blocks, triples, containing the special point in any pair of points corresponding to these endpoints. So you have 2n+1 points. And every time you have a black triangle that occurs in the decomposition, you take 2 blocks where the corresponding points on different sides. It's arbitrary, which, yeah, it doesn't matter. Just put the points in 2 columns somehow. And if there's a red edge, a triangle with 2 red edges, red edge kind of denotes the points here are on opposite sides, black edge on the same side. Well, I have to go on, but this picture explains that, for example, this decomposition of K4 with 2 colors into a single black triangle and 3 triangles with 2 red edges and a black edge is somehow, there's a Steiner triple system on 9 points in that picture. So you can calculate alpha and beta and get the necessary and asymptotically sufficient. This, another problem that's in the literature. A single graph, 2 colors, solid and dashed. You can think of the solid edges, of course, form a path of length 3, and if you complement that path, that graph in the 4 vertices, you get another path of length 3. And it's conceivable that you could find a set of paths of length 3 such that taking the complement of each gives you another decomposition. So first I want to partition the edges into 3 paths, and so that the complements do the same. It's equivalent to this graph decomposition problem, and you can calculate alpha and beta. This one is a favorite. Room squares. The rows and columns give 1 factorization of the complete graph. There are on my slide lines, grid marks, but you can't see them. That's all right. There are. It's a 7 by 7 array. And this is a skew room square because there is 1 symbol, 8, special symbol that occurs on the diagonal, and otherwise some cells are empty. Otherwise, if a cell contains a pair, an edge of the complete graph, these are unordered pairs. The opposite, diagonally opposite cell is empty. And so here's an empty cell, and this diagonally opposite contains a pair. And skew room squares, it took me a while to understand this, but they're nicer than room squares. Well, it's a little extra property, but they correspond exactly, in some sense, to decompositions, the graph decomposition problems. This is the graph. I have here, I had to go to directed graphs, and I have here 4 colors, let's say 4 colors, and the graph has directed edges of dotted color and directed edges of dashed color, a solid edge, black, solid, and you should think of this as actually as a pair of directed edges, so it has 2 solid directed edges, and the last color is wavy, and again, think of that as two directed edges in opposite directions, so that it has two directed edges of each of four colors. In fact, I prefer to think of it as two directed edges of each of six colors, because you may take the reverse of these dashed edges and call that dashed prime, and the reverse of these dotted edges, the other direction, call those dotted prime, and then you have six colors. And there is a correspondence to, I explained this very quickly. I'm leaving a lot of details out. But suppose you have an unordered pair of vertices other than 8, other than the symbol, a special symbol, for example, 3 and 7. So 3 and 7 will occur, there is a black, a solid edge joining 3 and 7. And that solid edge has to be in exactly one of the subgraphs that look like this. And when you find that subgraph, that tells you the dashed edges lead to the row you want to put the unordered pair XY in, and the dotted edges lead to the column. So, is it a skew room square? Does every unordered pair IJ, does one of them, row I, column J, does that contain, it should be either empty or contain an unordered pair, and the unordered pair should occur exactly once. It's strange, but true. As usual, I'll let you fill in the details there. So it's a very similar diagram, corresponds to what are called self-orthogonal Latin squares, which have, again, a special, no, they have all symbols on the diagonals, is that right? No, doesn't matter. You take row I and column J, and there's a black edge joining them, and you form a square array by putting this vertex that the dashed edge leads to. That goes in row I, column J of the Latin square, and from J, row I and J are now. It doesn't matter if I is row or column. What am I trying to say? This is well defined. That's what I'm trying to say. And I leave details to you, but that decomposition problem's equivalent. This one I didn't even draw. I think you need 12 colors or 6. With tournaments is another decomposition problem. It's self-explanatory. There are variations, but this decomposition problem is equivalent to what's called triple list. And that's good enough for a definition, and it's good enough for you to calculate alpha and beta. Steiner pentagon systems, a set of pentagons, you partition the edges into pentagons so that complementing the pentagon within each, that graph, with the complements of the pentagons within the 5 vertices form another decomposition of the graph. It gives you a design where lambda is 2. Every edge is in 2 of these graphs, once in the adjacent position and once in the opposite positions. Kirkman designs are actually equivalent to a decomposition. You must use, I think there are 6 colors there. Let's see. Solid, double solid, dashed, double dashed, and they're directed. And is that it? So 1, 2, 3. There's only 4 colors. If I had more time, I would show you the equivalence between a Kirkman design on n point, on 2n plus 1 points, and the decomposition of the complete graph. It's a little artificial. You must choose the first point first, first special point first. Resolvable reverse triple systems. That's even more special than Kirkman designs. These can be defined as designs, but it turns out to be the existence turns out to be equivalent to this graph decomposition problem. This is a generalization of reverse triple systems. How about if we go to designs of block size 4 on, well, 3 n plus 1 points for some n. And you ask for an automorphism that fixes one special point, and the blocks through that point, setwise, but permutes those in cycles of length 3. That I can go further. I can talk about design with blocks of size 5, which admits an automorphism fixing a special point and permuting the others in cycles of length 4. So this is a graph decomposition problem, and the asymptotic existence is decided by doing this computation. You have to look at those values of n for which this vector, it looks like I have 2 colors, black and directed red, but I prefer to think of 3 colors for some reason. I include the reverse of the red, so I have vectors of length 3 here. This graph, for example, has 6 directed black edges, 3 directed red, and 3 directed blue, opposite of red. So that corresponds to this vector. And you require this, and also n minus 1, the number of vertices in the complete graph, must be a linear combination of the degree vectors. Throw them all together. Don't worry which graph they come from. But this is a nice vertex. Notice that there's 1 black edge coming in, 1 black edge leaving, 1 red in, 1 red out, and 1 blue in, blue out if you do what I do and include the reverses. So that gives you, what's the vector here? I ran out of space, but its degree vector is 1, 1, 1, 1, 1, 1. So there's no constraint on n minus 1, sorry. But there is a constraint on n minus 1. So everyone knows that some of asymptotic existence problems in combinatorial designs can be attacked with the probabilistic method. This is very important and wonderful work by Peter Kiefausch and others. In particular, the existence of for concreteness, I seem to have designs with lambda 1 here. T designs, every T element set contained in a unique family of K element sets, so that every T element set is covered once. These are necessary and asymptotically sufficient conditions. So I will ask you if some of these methods can be used to obtain results on decompositions of edge-colored directed graphs and hypergraphs. And the answer is yes. The latest work I know about of Peter's is this one. But I think not everything. I don't think everything that we can do by our other methods is yet covered by these probabilistic approach. Here are some applications. 2 things that are known. It's always easy to, because they can be, the theory is nice because it unifies a lot of these things that were proved separately using certain methods, and you can simplify these greatly by just calculating alpha and beta for various families of graphs. Once you realize that there's a correspondence, the problem can be phrased in terms of the decomposition of graphs. So this one, for example, Kurt Chang's thesis under Ray Chowdhury in 1977 about the asymptotic existence of so-called group divisible designs. With the group, there's n groups of size G and blocks of size K. These are parameters. It doesn't matter what it is too much, but it corresponds. My point is that it corresponds to a graph decomposition problem, and that calculations give his result. The calculations aren't quite trivial, but still, his thesis was 100 pages or something, and it's never published, but it doesn't matter because it follows from this known result now. Here's something I like. Thinking in terms of graph decompositions, one can show that there are, like, you don't even need that for the first result. Result one is there are infinitely many cyclic designs with a given block size. K is given, that's the block size. And you want cyclic designs where there's a cyclic permutation that's an automorphism of the design. And a single, that's what you want, okay, and cyclic design. And there exist infinitely many for any block size. I wish I could say what the necessary and asymptotically sufficient conditions are, but I can't. So that this when you introduce the group, when you ask for cyclic designs or structures, the asymptotic theory fails. But at least you could say there are infinitely many. And that first result is known forever, I think, since 1973. But in terms of using graph decompositions, one can prove that there are infinitely, for any fixed block size K, there are infinitely many one rotation designs with that block size. So that does use the graph decomposition, but it needs cyclic decompositions which come from finite fields. And you don't get arithmetic sequences of orders, possible orders, which is infinitely many is nice to know. This first graph is simple. Between any two vertices, there's at most one edge. It's sometimes black, sometimes red, sometimes none. But just for fun, let me identify these two vertices and get another graph. And here it is. It's not simple anymore because these two vertices are joined by both a red edge and a black edge. So it's kind of a degenerate identification here, degeneration of this graph in some way. It's no longer colorized simple. And a graph like this was important in a result I'll mention in a minute. I didn't think it was interesting to consider decompositions into non-simple graphs. But colorwise simple, it came up in a problem. It was necessary. So now I'm talking about graphs which are not colorwise simple. And to discuss this, the existence problem, you need to talk about the so-called color set hypergraph of an edge-colored graph. So here you see an edge-colored graph. I have 3 colors, but there are actually 10 colors. You only see 4 here. 10 colors, and there are, let's imagine that you have 10 colors and a total of 30 edges that are occurring in pairs of parallel edges. And, you can form a color set hypergraph where the vertices are the colors, and this is not a edge-colored graph. And the edges are the sets of are the color sets. You see, I think that 1 and 2 are a color set because that's the set of edges, colors of edges coloring two adjacent vertices. And 1 and 3 would be a color set. So this hypergraph, in this case, is a graph. It's just an example I imagined. I'll come back to that. So this is a theorem of Lee Marcy, Lindner, Rania, and myself. I hardly understand what this means anymore, I forgot. 2, 3 perfect M-cycle systems, and whether they can be equationally defined or not. The hard part of this was proving that they cannot be equationally defined for other values. You wanted to, and to do that, it was sufficient to find an example of something. And that something example was a kind of degenerate collapsing of this graph where vertices are joined if they're distance 1 or 2. So to prove that, one had to come up with a decomposition of the complete graph into a graph with edges, red and black edges, complete multi-graph into copies of this graph, and this theorem will do it. Yes, if the color set distribution, color set hypergraph or color set distribution, this means the same, is resolvable, then you can partition this edge-colored complete graph, decompose it for infinitely many values of n. This condition resolvable, when this hypergraph is a graph, it's the same as saying it has a 1 factorization. And so let's look at the example. Here's the color set hypergraph, which happens to be a graph. Is it resolvable, or in other words, is there a 1 factorization? And you know there isn't. So this theorem says nothing about decompositions into this hypothetical graph here. This is incomplete, this result. Because it says, it gives a sufficient condition. If that color set distribution or color set hypergraph is resolvable, then there are infinitely many. But that isn't necessary. Here are necessary and sufficient conditions that, if given a colorwise simple edge-element colored graph, that decompositions exist. Some multiple of the color set hypergraph must be resolvable. It took me and others a long time to realize that this you had a sufficient condition, but what was necessary, and this is it. So going back, this may not be resolvable, but you know, twice the Peterson graph is resolvable. So, and 3 times is not, but 4 times is. Odd multiple of the Peterson graph, repeating each edge, giving it a multiplicity. For the proof of necessity, notice that if you have a G decomposition with T copies of G, then T times the color multi-set hypergraph of G is resolvable. I'm going to have to speed up and omit even more details. This is a picture, a theorem of Amidrak, Ganova, and myself. These conditions, we give the necessary and asymptotically sufficient conditions for the existence of G decompositions for color-wise simple edge R-colored graphs. And there are applications of this too. This is some stuff about the proof. You need some notation to say this well, so you work in modules of formal sums of subsets, and a partition is a set of sets. Think of it as a sum, a formal sum of 3 sets. And then you can state things, and there are some, this module, there are some resolvable elements. This is thinking about 5 colors. And that equation here is very important for simple, but very important for understanding the necessary conditions and getting them right. So I may have said that before. It's very interesting, but I think I'll skip it. Anyway, this example, which again I haven't written out completely, this is this graph with 30 edges and 10 different colors. If you calculate alpha and beta as we knew how to do before, you get beta is 6. Excuse the mess I made up there. Beta is 6. But that's not going to work. You need beta, it will only work half the time. Beta prime, the correct value, is actually 12. That comes because the Peterson graph is not resolvable, but twice the Peterson graph has one factorization. So next you can talk, I haven't talked about Colorwise simple edge-colored directed graphs. That I leave. I don't define it. We can do this though. And finally, we get rid of the Colorwise simple and consider complete graphs where any pair of vertices is joined by 7 edges, 9 blue edges, 10 green edges, some fixed number, and graphs which you want to decompose those into. We can explain what the necessary and asymptotically sufficient conditions are. And here's an application. This was known before, 1984, but we need to consider graphs. It's equivalent to graph decomposition problem where you have quite a few edges of one of each color and lambda edges of each color joining any 2 pair of vertices. That's an ugly complete graph. So to do that, the proof gets a little harder. You have to introduce bi-color sets, bi-partitions, and bi-resolvability. And I don't think I have any more slides, so I will stop here and thank you for your patience.
Thank you very much. We have time for a few questions, comments, if there are.